Well, today I'm going to do an example, or at least start you off on the set 13, second order modeling, and problem 2. It's about an LRC circuit. Okay, that's inductor, resistor, capacitor. Okay, so a capacitor in an LRC circuit has a charge of 6 times 10 to the minus 9 coulombs. And here's the situation for T negative before we start the experiment. There's an inductor. I don't know why they call it L, but L for inductor, resistor, and capacitor. Now this resistor is a variable resistor, so it kind of has a knob you can turn. And it's got this charge on it. And I've indicated the plus and minus charges on the capacitor. And they can't flow because this circuit is open. The switch is open. Okay. Okay, at t equals 0 seconds, the switch is closed, boom. Okay, and current starts to flow. All right, so here's a little picture of the current I. It's going counterclockwise here. These plus charges are rushing around because now the circuit's closed, they can go. And eventually, the charge, the charge on the capacitor will go to 0 if there's any resistance. We'll see that later. Okay. The current through the resistor and inductor is I for current, and that's dq dt. So the rate of change of the charge on the capacitor, when charge leaves the capacitor, it's current flowing around the circuit. Okay. All right, and I is measured in amps. Okay, Q of T is the charge on the capacitor. Kirchhoff's laws say that the voltage drop across the inductor, L di dt, plus the voltage drop across the resistor, Ri, plus the voltage drop across the capacitor, Q over C, is equal to 0. And that's for T equals 0 after we've closed the circuit. There is a voltage drop before, that's Q over C, before I close it. But then as soon as I close it, current starts to flow and there's no voltage drop. So the question is, what is Q of T for T positive? Under two circumstances, one is when R equals 0. So there's no resistor, that's just an LC circuit. And then, or we also have R is critical value. Okay, that's R, that gives a critically damped oscillator. We'll talk about that later. Okay, so I'm going to erase a lot of this stuff. The only thing I really need from this is this. Okay. All right. So I can get a differential equation for Q by replacing I with dq dt. So d dt of dq dt is d squared q dt squared. So the ODE is L d squared q dt squared plus R dq dt plus q over c equals 0. Okay, so this is the second order linear homogeneous ODE with constant coefficients. So we know how to solve those. Let's think about the initial conditions. So you have, the initial conditions are, what is the initial charge? I have Q at 0 right before I open the switch is 6 times 10 to the minus 9 coulombs. Actually, capital C stands for coulombs here, and it stands for capacitance here. So SUNY, but that's those are the standard notations for those things. And what is Q prime of 0? That's the initial current. What is the current flowing at t equals 0? Nothing. 0. So basically, we want to solve this guy. Okay, so we solve first for r equals 0. Well, that means that L d squared q dt squared plus q over c is 0, or d squared q over dt squared plus, I'm dividing by L, plus 1 over LC q is 0. So omega naught in this case is 1 over LC inside the square root, right? This is omega naught squared. And then you know how to solve that. I won't go into that a whole lot. Okay? Now let's think about R positive. When resistance is positive, what we get is the characteristic equation. L, little r squared, plus big R, little r, plus R over C is 0, right? Okay. So, right, this is for Q is e to the r, T type solutions. So we get this quadratic equation for the root r. So the critically damped means that the roots are repeated. In other words, r is minus b plus or minus square root of b squared minus 4ac over 2a. You know what I mean. There's a, there's b, there's c. Little c is actually 1 over c in this case. So the idea is you can find out what r has to be by computing this quadratic equation solution for r, and we want the thing inside the square root to be 0. You set b squared minus 4ac equal to 0, and solve for r, the resistance, and that's the critical resistance. Okay? All right, so I'm not going to go through the whole problem, but you're going to do that, and then you're going to solve for Q of t in these two cases. One, when the resistance is 0, and one, when the resistance is just what it has to be to get repeated roots of a characteristic equation. Okay, so I'm not going to do it all for you, but when you're done, you're going to get an answer in terms of your L and your C that your problem has, right? So your frequency will be 1 over your LC, and then the period that they asked for is 2 pi over omega naught. And you're going to use, you're going to have your omega naught from your random inductance L, capacitance C, and your period, okay, will be that. Okay, in fact, I can even write it. It's 2 pi square root of LC if I invert and multiply there, okay? So you can see the period increases with L and increases with C. And by the way, you're going to find this period is a really small number. This frequency is huge. There are millions of cycles per second, right? So in fact, that's why we can be doing with this. We're talking to each other now because the clock cycle in our computers is so fast. We got all these oscillators flipping around millions or billions of cycles per second, right? Megahertz is million cycles per second, mega, okay? And that's what allows us to do all this great stuff we do. We can be separated by distance and time, but I can still tell you about this problem because of the wonders of electronics, right? Okay, well, good luck on this. I'm not going this thing through to completion, but I'm sure you can do it now with this help. All right, bye.